We are looking now at exponential and logarithmic parent function graphs, and then we'll apply transformations to those. We have looked at a variety of different parent functions in the past. So these two are two additional ones that we want to add to this list that we already know. The first one is an exponential parent function graph. And so this is the one on the left. The standard form of this is f of x equals a to the x, okay? And a has to be greater than 1 in order for it to follow this shape. Notice that this shape starts off kind of slowly from left to right, and then it rises exponentially. This basically models a lot of different things in real life, which you can get to in other problems, and we've even talked about with compound interest. That is modeling an exponential growth, okay? The base of this A, determines how fast it goes up, okay? And in a very similar way, that is the basically the stretch of this. So let me give you a quick example. This graph specifically is 2 to the x. I want you to think about that again, because this is exponential, the x values we're plugging in are the exponents for this. So if I have 2 to the x and I pick an x value of 0, 2 to the 0 is 1. Remember, that's a really big important math rule. Anything to the 0 power is 1. And so no matter what our base is, you're always going to have this point 0, 1. That is your big reference point in this parent function graph. As we had many reference points that were normally 0, 0, here this is the one we care the most about because it applies no matter what this base is. If that was 3 to the x, 3 to the 0 is 1. So no matter what the base is, you're always going to have this 0, 1 point. Now, your other point here, 1, 2, comes from the base because your x value is 1. So if I do 2 to the first power, I'm getting out 2. So whatever the base is, if your x value is 1, your y value is that base. So in this case, that would be 1, 2. If that base was 3, this would be 1, 3. If it was 4, it'd be 1, 4, and so forth, okay? So you would see it going up taller and taller and taller. All right, so that's the general form and the basic shape of our exponential parent function graph. Let's move to our logarithmic parent function graph here on the right-hand side. You see that our basic function here is f of x equals log base b of x. And again, b is greater than or equal or greater than 1. Notice that this kind of has a similar shape but flipped kind of the opposite direction. And this is because exponential and logarithmic parent functions and functions in general are inverses of each other. And so we have previously talked about inverses. Inverses is if you have xy on the original, you can flip that to make yx on the inverse. And these are a perfect example of that, okay? Exponential and logarithmic functions are perfect examples of inverse functions. So how does this apply to this? Well, if our original was 0, 1, then our inverse, our log function, is going to be 1, 0. As you see that x and y flipping. In the same way, if I have 1, 2, and I flip that, I get 2, 1. So this specific graph is log base 2. How do I apply this base of 2 to this problem? That's going to be the x value of 2 and when your y value is 1. So basically the exact opposite of the exponential. And you will always, in all these logarithmic function graphs, you will always have 1, 0 as your reference point. So your main reference point is 1, 0 for log graphs. And then your base tells you how far right you go when you go up 1 unit. So if your base was 3, you would be here at 3, 1. And it would go more like that. If you were 4, it'd be like that. Okay, so this is kind of doing that stretch, but horizontally, again, because this is inverse function, okay? And remember, it's kind of reflecting over this line. So if you look at that y equals x line, it's reflecting over that. So that's kind of the comparison between the two. Now let's look at a few specific examples of being able to see a graph and determine what its graph actually will be once you determine the base and things like that. Okay, so let's look at some examples. All right, so we have two different graphs. These are both exponential graphs, so I will go ahead and tell you that. And we need to find out what is the actual function for this. We know it's exponential, so we know it's in the format a to the x. How do we figure this out? Well, let's first check. If this is exponential, it goes through the point 0, 1. So does this first one go through the point 0, 1? It does. Now, how do I figure out the base to this? Again, remember, this is if I have a to the first power, that gives me a. So if I plug in x equals 1, what I get out, that y value, is going to give you the base. How do you do that on the actual graph? Go to x equals 1, go up to the y value of where that graph cuts across, x equals 1, and that y value, which in this case is 5, so you have the 0.15, that 5 is your base. So this would be 5 to the x power. Okay, so again, 5 to the 0 is 1, 5 to the 1 is 5. All right, let's look at this other one. This one is the exponential shape, but clearly it's going up on the left and not the right. So let's talk about how that happens. This goes through, again, the point 0, 1. So we know it's going to be a to some power. However, with this, we're not going to be able to go over to the right one. Okay, so our x value of 1 only gives us some decimal that we don't know. We don't know. So I want us to think about this. If this is taking the original function that would normally look like this and flipping it to look like this, that would be flipped or reflected over what? So this is taking all those transformation rules you've already learned and applying them. And so I want you to go way back in your mind and remember that if we flip it from left to right, that is reflecting over the y-axis. Where does that apply? What are you going to do in the function to make it like to be able to account for that? And so in the function, to account for a reflect over y, remember that is a negative on the inside. And now we don't really have, it's kind of hard to see the inside here. We don't have parentheses or absolute value or anything like that. So I'm just going to tell you the inside is up in the exponent. Okay, so if I say, hey, I want the negative to be inside, I'm talking about a negative right there. Okay. All right, so how does that impact how we figure out the base? Well, if I know this is reflected over y and I have a negative up in the exponent, then when I try to figure out what to plug in, I need to plug in something that makes this x, like when I plug in an x, it makes the exponent all positive. And so if I plug in -1 here, then I have a to the first. And that will give me my base. Okay, so again, what did I plug in for the x value? I plugged in x equals -1. So we're going to go here to x equals -1. So long story short, I did all that explanation to basically say, if it's reflected over y, look at x equals -1 instead of x equals +1. Okay, that's the shortcut of all of that. All right, so let's go up. For at x equals -1, we're going up to where it crosses. And so it's crossing here y value of 3. So this is -1, 3. That means that our base, or a, is 3. So this would be 3, but 3 to what? Again, this is reflected. So we're going back to this. This is 3 to the -x. This is 3 to the -x. Also, as a quick note, sometimes the computer, depending on what program you're using or whatever, may write this as 1 over 3 to the x with no negative there, because Go back and review those exponent rules. If you have a negative and you want to change it to a positive, it has to cross the fraction bar. So if I have 3 to the negative x, I got to bring it down to the denominator to take that negative off, which means that I now have 1 over 3 to the x. You could also rewrite this as 1/3 to the x, because 1 to the x is really still just 1. 1 to the 7th is 1, because you're just multiplying ones all together. Okay, so you can see this in a variety of different formats. The answer for you depends on whatever problem you're using and whatever program you're using. All right, so again, if it's reflected, look at the -1 version of x, not the positive one. So that's kind of the shortcut to that. That was our exponential graphs. Certainly these can move up, down, left, right. That reference point of 0, 1 is what you're looking at to determine that. Okay? All right, let's look at a log graph real quick. And this one, we go a little bit easier on you. I apologize, the graphs are a little blurry, but we should still be able to figure this out. We are looking for the graph y equals log base 5 of x minus 3. So first I want you to tell me what my base is. Base here is 5. Then I want you to use all the same things that you learned with transformations to tell me, what is this minus 3 going to do? So for any parent graph, what's the minus 3 do? It takes it down 3 units. Okay. Lastly, I just wanted to give you a reference here. Some of y'all might have said right. Okay, just remember your inside is actually going to be inside the parentheses with a log function. Okay, so for exponential, inside's up in the exponent. For log, it is truly in the argument inside those parentheses. That said, what is our reference point if we just had log base 5 of x? Remember, our exponential reference point was the point 0, 1. So our logarithmic reference point here is going to be 1, 0. And so that's the moving that we're doing. If I go to 1, 0, then go down 3 units, I want to see if that point is on the graph. That's how we're determining this. So I'm going to go to 1, 0 on each one of these, not 0, 0, 1, 0. And I'm going to go down 3 units. So 1, 2, 3. I don't see a point there. Let's go to 1, 0 and down 3 units. 1, 2, 3. No point there. Let's go to 1, 0 and down 3 units. 1, 2, 3. I have a point there, and so this would be your correct answer. Okay? I do want to say this is not correct because your log is going to be like that. And as a quick rule, if you just need to remember your general shape, this may help you, it may not. I don't know, but if it does, great. Then a to the x, or any number to the x, is the graph scoops up like an exponent. Log base, let's say b of x, this b, if you start at b and go towards x, that's kind of what it looks like. So you're looking at a graph that if you had both of them, it would look like this. Actually, that's not correct. Hold on. It would look like this. This is your a to the x. This is your log base b of x. Okay? All right. So know all the same transformation rules as you did with all the parent functions.